Right, great. Thank you very much. Thanks for having me. Thank you for being here today. We're going to switch tradition, as you can see. There's slides, no Blackboard talk. And I was asked to tell you a little bit about approaches to waveform modeling. So this is going to be an exclusively compact binary focused talk. Sorry to everybody if it doesn't work on compact binaries, but I do hope you do find them interesting eventually and maybe want to dig in with them with some of the hands-on exercises later on in the week. So the plan, there's 3 lectures this week, 1 today, 1 on Thursday, 1 on Friday. And my plan, at least, let's see how it goes, whether it goes to plan or not, is the following. Matthias already introduced you to linearized gravity this morning and the quadrupole formula, but I thought it might be useful to just recap a little bit for a couple of minutes, connect the things, and in particular, to then hopefully navigate you through what is called post-Newtonian theory and post-Minkowskian theory, which are 2 of the main perturbative methods that we use to describe the gravitational waves from compact binary coalescences. Well, not the coalescence in this particular case. It's just focused on the in-spiral part, but it's really, really fundamental. And it's an ingredient that we then use later on to construct these full waveform models, in-spiral merger ring down or IMR, that are really kind of bread and butter every day when we do gravitational wave data analysis of the LIGO data at the moment. So I want to spend a little bit of time on that. Big disclaimer, I'm not going to derive all these things. If you have ever looked at the PN paper, right, you will see there are I know this is recorded, so maybe I shouldn't say that, but they're quite horrendous expressions sometimes. But my goal is for today to kind of walk you through some of the crucial pieces and elements and kind of guide you a little bit of a roadmap, like you'd be driving along a card course. So you kind of see what the elements are and then introduce it to some of the post-Newtonian approximants that we actually use either directly for analysis, like Taylor F2, which some of you may have come across before, or we use them, as I said before, as crucial inputs to then build on them and make better and better waveform models for binary coalescences. And then we'll see how far we go. But from that, we take it on to the effective one-body formalism, which is a very successful formalism which takes our PN waveforms and pushes their validity further. And when I say further, I mean further in frequency, and that means pushing it closer to when our 2 objects eventually are going to collide. It doesn't push us all the way. It can, not very accurately. And then we can do further things like calibration to numerical relativity simulation in order to make it better. And so we then transition over to NR. I'm not going to introduce it to numerical relativity because there'll be dedicated lectures next week. So if you have looked at the schedule, you're aware of that. But I give you a brief summary so we can talk about surrogate modeling, which is a term essentially just telling you you have a slow waveform model. And by slow, we mean computationally slow, because that's one of the elements that really matters for us in everyday data analysis. And we make it faster. And numerical relativity simulations are notoriously difficult to simulate across the parameter space, right? People have made a tremendous progress in the 20 years since it's been possible, when we had the breakthrough in 2005. But there's still, we don't have a continuous coverage of the binary parameter space, and you can make this more and more complicated, but that comes with a lot more challenges, right? So having discrete data sets, discrete simulations using reduced order modeling techniques allows you, at least in a limited sense, to build waveform models that are based on numerical relativity entirely, but are also feasible to actually use in data analysis applications. And then we move on to phenom waveform models, or phenomenological waveform models. Is a mouthful, so phenom, and anybody says phenom, and I say phenom, that's what I'm talking about, where we combine now different methodologies together, in particular the post-Newtonian approach, and then numerical relativity simulations, and maybe some insights also from black hole perturbation theory in order to actually create the full waveform model. So we talk about these. And then once you know, so these are the 3 big families, essentially, that we are used in everyday compact binary data analysis applications. And then we'll see how much time is left to talk about some of the physics that we model in those models. Obviously, we want everything. We cannot have everything. We make approximations. So something I have specifically been working on for a while is how we model spin-induced orbital precession. So some of you know this as the Lense-Thirring effect, right, where the plane starts to wobble because of the coupling between the spins of your black holes and the orbital angular momentum. And that induces cool effects makes the dynamics a lot more interesting, the waveforms a lot more interesting, but the modeling problem also a bit harder. And so we're going to talk a little bit about this because there's essentially a singular framework that is used in all the other models here that we then use for data analysis. So that should give you a good sense of what is practically done on the side of waveform modeling, at least at the moment. Now, these exercise or hands-on sessions that Matthias mentioned earlier this morning, for the particular stuff I'll be talking about, I thought what you could attempt, depending on how interested you are in which camp you're kind of landing, what sort of experience you would like to gain, that's entirely up to you. But you could delve into deriving a PN approximant. But that I don't mean carry out crazy high-order PN calculations, but actually somebody gives you a flux, our PN friends give us flux and energy, and we can compute for the energy balance equation the actual phasing of the waveform. And you can do this in different ways, as we'll see later on today. So this is a good thing, which you could try hands-on. In particular, if you have Mathematica installed on your laptops, that can be quite handy. You could also build a simple phenomenological model or use tools that are available publicly to you to build a surrogate model. Numerical relativity data, for example, is available publicly as well. So you could try, how does it actually work? How can I build a phenomenon or a surrogate model? So we can do that. And then there's a little tutorial notebook that I've thrown together with my colleague, Gary Pretton over there, if you want to play around with what's out there. Many of the waveforms are publicly available to you that we use in the data analysis framework every day, either through something called LAL simulation or newer version also in Python is GW signal. And so you can play around and learn and discover the physics, what it means, what happens to the waveforms if you change parameters, what's the impact on the energy distribution, kind of think more about rather than building it, now I use a model and analyze data with it, what does it tell me? And what sort of physics can I learn from it? So that's the roadmap. I hope that sounds all right to everyone. Suggested reading material. So especially for the PM part, you will see the notes here now, which, as I said, is not a derivation of anything, but me trying to kind of signpost you and navigate you around the tools of post-Newtonian theory. And the key ingredient into waveform modeling follows Luc Blanchet's very big living reviews in relativity article that you can find for free on the internet. If you have never read it before, I can recommend it highly to you. There's, of course, standard books which focus on the analytic side of things, and then other review articles, and we'll dot around some papers as we go along as well. And of course, many of these will have very interesting and exciting references therein. In particular, if you look for a particular post-Newtonian order or something like that, you might want to take a look. So with that logistics out of the way, we have already heard there's different astrophysical sources, right? Matthias mentioned compact binaries already in the morning. Bruce just now talked about stochastic gravitational wave background. I will be exclusively focusing here on compact binaries. And in fact, you'll see I will actually probably not at all talk about tides. So nothing with matter in the system. Apologies to the people who work on binary neutron stars in the audience. But for setting the scene, we'll make it simple and easy in quotation marks and just focus on binary black holes. Of course, you can model other sources as well. So just because I'm talking about approaches to waveform modeling, don't think you cannot model other gravitational wave sources. In particular, supernova waveform modeling for numerical simulations is big business as well, especially from Quad Labs. And I believe there are lectures next week, if I'm not mistaken, to tell you a little bit about supernovae. Maybe they also cover the waveform generation there. But for today and the next two lectures, it's going to be binaries. All right. You have probably already noticed from the way I talk, I work in LIGO, so I do feel very strongly obliged to show you our kind of, not quite state of the art, but after the third observing run, our kind of detection plot, essentially, and draw your attention to all the blue dots, which are the binary black hole coalescences that were identified by the LIGO-Virgo-Cargo collaboration. Obviously, we have colleagues here who have done their own searches, conducted their own searches, have found additional signals. So I encourage you all to take a look at that. But this is just really to set the scene, because when you look at this, you should ask yourself, okay, this is a lovely mass plot. How do I learn about the masses? What is the machinery behind actually extracting all this astrophysical information, which I think most of us who are in the business are after, right? We're here to do the astrophysics. So how do we get there? Now, for compact binary coalescences, waveforms really are at the heart of it. So having a theoretical prediction of what the gravitational wave signal looks like to very, very high accuracy, and how accurate it has to be, that's still an open question, is really, really fundamental. And we need that essentially for three big steps in the whole machinery of analyzing data. First, if we perform what is called a modeled search, we need these binary waveforms for the detection itself. You do not need that everywhere in parameter space. You might not need all the physics included in those. Right now, we don't do that, right? Banks that the LVK uses and most other colleagues outside as well will only have a limited amount of physical effects included in them and still doing a pretty decent job, right? But eventually you want to learn about the masses, the spins, the astrophysical environment, where are these black holes and neutron stars born? How do they collide? What's going on with them? And for that, we perform inference, and you'll have lots of lectures this week where you'll see how Bayesian inference on gravitational wave data works. For that, we really need highly accurate waveform models when we talk about compact binaries. And some of you might be interested in performing tests of general relativity. Right, well, so if you want to test GR and not falsely claim a violation of GR for some of the tests you're carrying out, you might want to have a very excellent prediction of GR in the first place if you're looking for a deviation. And right now, models are not perfect. I hope I'll convince you at the end of the week that we're doing, that we're working towards getting better and better models, so to say. But they are not perfect, right? They have mistakes in them. They have errors. We use approximation methods. Right now, most of our analyses, I would say, are still dominated by statistical uncertainties, purely coming from the noise fluctuations in the actual data that we have. But we are starting to see systematics between different waveform models, right? We have all these great families that you'll be familiar with by the end of this week. They don't always give us the same answer. Which one do you trust, right? What if you use one and it turns out there's some intrinsic one-directional systematics that pushes you in continuously in the same direction, and so on and so forth. And so approaches to waveform modeling are really, really crucial, because systematics can become the limiting factor, especially as we go forwards with increased sensitivity in our detectors and signal-to-noise ratios, right? If you think 3G, I hope many of you are at least following developments around Cosmic Explorer and the Einstein telescope. We really need much better precision in the waveforms than we have today. So the eventual goal of all of this is this, essentially, which might look very simple, but it's just a beautiful wiggle, isn't it? Hope everybody thinks very beautiful, where we have the classic chirp signal. That is the fingerprint, the ID of any such compact binary coalescence that we observe. Where we have the early in spiral here, and we'll be focusing on the modeling techniques for that part of the evolution for today. But at some point, these analytic approximations, they start to break down. They blow up, they literally have divergences. They do not converge. So you have to do something else. And yeah, the nonlinearity of GR strikes back, so to say. So what we do is we solve the full two-body problem in GR numerically, and then eventually what we end up with is a perturbed black hole in this particular case, where you can get some information from black hole perturbation theory, but not all of it. In particular, the amplitude scale, you still need input from numerical relativity simulations. Yeah. Now, if we translate this time domain evolution here of an in-spiral merger ring down signal into the frequency domain, I hope most of you have seen a plot similar to that before. So here we're just looking at the amplitude, but now the frequency domain amplitude for three different signals. They're all compact binary signals, but I've scaled them by their mass, by their total mass. And as Matthias was saying this morning, the total mass sets essentially the frequency range of your signal. And our detectors have a limited bandwidth, right? They can't observe all frequencies. So here you can see current generation of ground-based detectors, which is somewhere between 20 Hertz and a few kilohertz in terms of the frequency range that we're sensitive to. And if we stick in a binary black hole merger, here I think this is a 10 plus 10 solar masses. I think you can just about see the merger in band here. Whereas if we go for binary neutron stars, so 1.4 and 1.4 solar masses, all you essentially observe is the in spiral, with the late stage of the mergering down being out of band. It still merges, of course, we just can't see it. So I'm pointing this out because depending on what class of sources you're after, you might not care about certain parts of the modeling problem so much, right? And you might want to put your emphasis on making aspects more accurate in a different place. So just do keep that in mind. All right, you're all familiar. Nobody has written down the field equations today so far, which is surprising. so there you go. Obviously, we have the Einstein tensor defined as the Ricci tensor minus 1/2 the Ricci scalar times our metric, g mu nu, and that's including g's and c's, 8 pi g over c to the 4th, times the stress energy tensor of the sources that you're considering, right? And in Wheeler's words, space-time curvature tells mass how to move, and mass tells space-time how to curve. Now, this looks beautifully elegant in the covariant form here, of course, but if you look more closely and you actually want to solve these, right, these are 10 coupled nonlinear PDEs. Everybody is familiar with that. And how are you going to solve this for a two-body problem, right? Not with pen and paper, at least not for the accuracy that we need. And so there's essentially two ways. You do it exactly, and I put this on purpose in quotation marks, and that's probably deliberately, how should I say, cheeky. Because of course, people will say, well, if you do it numerically, you have no approximation methods, you actually solve the exact system of equations. You still have to find initial data, right, that are appropriate. You will have numerical approximation errors. Those can accumulate. So numerical relativity simulations, even though we try to make them as accurate as possible, they still come with an error budget, right? So do also keep that in mind, because sometimes you hear people saying they are perfect. They're not. Some codes might be more perfect than others, but they definitely have an error as well, right? And then, of course, there's the approximate way of solving such a complicated system of equations through different perturbative methods. And I'll tell you about those in a minute. In practice, as you have taken from the previous slide, we need everything, right? We combine all of these methods essentially together to get the full waveform models. Now, where do you use what? That's the question, right? And barely anybody does everything simultaneously, but you can split the problem kind of up in this way. And that's a very nice slide that Harold Pfeiffer made that I stole from him from one of our Einstein telescope presentations, where you can see the mass ratio, so the relative mass between your primary and your secondary object. And here on the x-axis, you can see the frequency. So in spiral, evolution to merger, frequency increases, right? Mass ratio here from equal mass to very, very unequal mass black holes, right? Supermassive black hole and the tiny stellar mass black hole falling into that. And you can see here indicated our three stages: in spiral, merger, and ring down. And so this is kind of the toolbox that we have. If we are in the regime where we have two objects that are very, very far apart, they still be two black holes, doesn't matter, but they're very, very far apart, we can perturbatively approximate space-time and the motion therein and the gravitational wave generation in the context of post-Newtonian and post-Minkowskian theory. As you'll see later on, does not really have such a strong dependence on the mass ratio. And in fact, at very extreme mass ratios, we can start to compare it to extreme mass ratio perturbation theory or gravitational self-force at the end of the day. So this is very good. We have a significant amount of overlap here, which when you do some sort of analytic approximation techniques is very handy, right? Because you can compare your results. Do you get the same answer? Job done well. And in fact, sometimes it's very difficult to compute all orders in a particular expansion series. And so drawing information in from another technique can help you to complete the problem at a particular post-Newtonian order. All right. Numerical relativity, you can see up in the box here, this is not a fundamental thing that we cannot, you can solve numerically an extreme mass ratio situation. Just at the moment, the techniques that we have, it's not really possible to do that, right? So there's something called the Courant limit, which tells you the ratio essentially between your time and your spatial time stepping, and that is significantly penalized the more unequal mass your binary is. And so this, at the moment, I would say at least numerical relativity simulations, there are a few dotted around the up to mass ratios of a few hundred, but beyond that, and as I said, individual dot points. I think there's maybe 5 simulations we could count on our hand. So in that sense, we're kind of technically limited, not fundamentally limited at the moment. And then for the very last stage, as I mentioned before, we can do single perturbed black hole perturbation theory. The only thing we need to be careful about is the attachment to merger in terms of setting the actual scale of the size of the perturbation. So we have 3 stages. Let's get started with the first one, right? And that's the in-spiral part. Now in that plot, it said PN theory and post-Minkowskian. So what are these things and what are the kind of fundamental assumption behind it? They're both particular series expansion techniques, and I will try to walk you through how they work. They make particular assumptions. Post-Minkowskian, post-Newtonian theory assumes weak gravitational fields and slowly moving sources, which makes sense, right? When we are in this in-spiral regime where we have far separations, right? Things are not moving close to the speed of light. And the gravitational field, even though the objects themselves have a strong self-gravitational field, right? But the field kind of that we are dealing with overall can still be considered relatively weak. Post-Minkowskian theory, on the other hand side, only assumes weak gravitational fields, doesn't necessarily make an assumption on how fast your sources are moving, right? And when I say slowly moving, of course, in my head, there's a binary, right? So the velocity is, of course, the orbital velocity that we are talking about. But in principle, you could think about any sort of intrinsic velocity motion that characterizes whatever your source is, right? If you don't want to think about a binary system, that's kind of what we're talking here about. And then kind of taking this and pushing it further, does the uncalibrated effective one-body formalism, which literally is a generalization of the Kepler problem that you like to think of, right? So our one-body formalism in Newtonian gravity and maps it essentially to GR. Now there's a lot more subtleties in there, but that's what you kind of should be thinking about. And I on purpose put here uncalibrated because we make it really to what we use in everyday data analysis by including a lot more non-perturbative information from numerical relativity. But there's a whole lot of other approaches, and some that have become very popular in recent years because higher order post-Newtonian and post-Minkowskian calculations in the traditional framework are hard. They're very difficult. And it has been found that other approaches to the two-body problem, using, for example, effective field theory, or more recently also techniques from QFT in the form of scattering amplitudes, can actually help compute these higher order terms in a more efficient way. So I will not be talking about this, but this is a really interesting development in recent years. And if you are interested, there are very nice review articles out there, for example, by Rafael Porto on the EFT approach. If that's something you're interested in, I strongly recommend taking a look at that. And then, of course, as I've mentioned before, if we go to the extreme side, we have gravitational self-force, which is the bread and butter tool that is being used for extreme mass ratio in spiral. So if you are a LISA person and you're interested in those sources that are not accessible in the current generation of ground-based detectors, then probably that's what you would look into. There's the black hole perturbation toolkit, which is a public code, for example, a toolkit that you can use if you want to play around with generating Emery waveforms. And then very, very classical, of course, traditional black hole ring down perturbation theory. All right. So as I said, I use as a basis for my roadmap to guide you through post-Newtonian and post-Minkowskian approach, Luc Blanchet's living reviews. And so these are the conventions, notations that are being used, which is the traditional one where we have a sign of the signature of the metric, which is 0, which is minus, and then 3 pluses. So sorry if there are any particle physicists in the room who like it the other way around. Sorry. Greek indices are going to denote space-time indices, so 4 of them, including the time component, and Latin indices are purely spatial. Okay, so that's hopefully consistent. If you spot any mistakes, please do shout out. And with that set of definitions, right, then we have the Riemann tensor defined in the normal form here, where x is here just denotes some coordinates that you choose, and the gammas here are the Christoffel symbols, and the Ricci tensor is the 1-3 contraction of the Riemann, and the Ricci, then the contraction of the Riemann tensor. And T mu nu, capital T mu nu in all of my notation, is going to denote the stress energy momentum tensor of the source. There will be another one appearing later on, but that is really of the smooth matter source that in principle we will be considering. Okay. All right. Now, the starting point for this traditionally would be linearized gravity, right? Which you have seen this morning. You all know, I think, so we can very, very quickly skip through this, where the idea really just is we want to understand how gravitational waves are produced when we essentially just consider Newtonian or at most special relativistic dynamics, right? There's no back reaction taken into account here. And so the assumption is that we just have gravitational fields that are sufficiently weak and we allow to expand around flat space. And that's what Matthias wrote down this morning. And I think Bruce also was assuming linearized gravity, if I'm not mistaken, right? You work this through, you choose a particular gauge, and then you end up with your field equations in that particular form, which you have all seen, where h bar denotes the trace reverse tensor here. And on the right-hand side here, again, we have our stress energy tensor. So that's a wave equation, very nice. And box here is just the flat space Dillon version. If you choose the Lorentz gauge or harmonic gauge, different names here, then you'll find that the equations of motion, right? So the stress, energy, momentum conservation laws are those of flat space. All self-consistent so far, right? Nothing's changed. Now you want to solve the wave equation. You all know how to do that. Method of Green's function, right? So we plug it in here. Matthias showed you also this already this morning. And in particular, if you get your boundary conditions right, you'll see the only solution is going to be the retarded solution to that, which essentially just tells you you're considering a source that has no incoming radiation in the infinite past, right? And they are also known as the Kirchhoff-Sommerfeld boundary conditions here. So that's kind of one of the assumptions. I don't know, sometimes this is a bit swept under the rug. But that's why we only have essentially the retarded solution selected here. Now we do what Matthias did in the morning and drew very nicely on the board. We consider our source and we consider a point very, very far from the source. So our distance r is always going to be the little distance. It's just this position vector, north of the position vector. And if my source is now moving very slowly, I can do exactly that, right? I can do the multipolar expansion of the retarded time and the denominator here and plug it back into my equation. And then we choose the particular gauge that you have also been introduced to this morning already, the TT gauge, the transverse traceless gauge here. And what you end up with is your metric perturbation, which is now purely spatial in that gauge, right, is proportional to 1 over the distance. And then we have this object here, which is your projection tensor along the line of sight, so towards your observer n, where n is literally just the unit vector along x. And we have our t expanded source tensor here, right? So we remember the expansion here of the retarded time, as we've done already this morning. And it turns out you can write this as this very nice series. And you will notice here already that this is a series in kind of expansions that have 1 over c to some power terms, an ordered series, right? You'll see we have a leading order term, and then we have a 1 over c term, a 1 over c square, and so on and so forth, all evaluated at the retarded time. Now the question is, what are these weird tensors here that are appearing from the expansion of my stress energy momentum tensor? Well, they are exactly that. They are the moments of the stress energy momentum tensor, and people in the literature, you'll find different notations. I've just generically called them S here, where we have the integration here with Tij, then we have Sijk, where we've also got the position vector times 2, and so on and so forth. And you can make this a little bit more explicit, right? And write these out here in terms of the mass and the linear momentum. So this, I think everybody has seen this before. It just comes back to the point that we had this morning, right? That our gravitational waves are sourced by some multipole terms here that come from the expansion of the stress energy tensors, and we can very nicely relate those to some intrinsic properties of the source, which you kind of would expect, right? It makes sense, right? Depending on what you have, it's going to generate a different kind of gravitational wave. And if you work through these general expressions on the previous page, consequently, then you'll find, to hopefully nobody's surprise, that the time derivative, right, of the monopole, so m, is 0, which corresponds to the conservation of the total mass of the source. And the time derivation of your angular momentum, of your linear momentum vector, is also 0, because that is also conserved. And you work it through, and after systematic rewriting, you find at lowest order, so our first term here, this term here, the lowest order term, right, the one that doesn't have a c anywhere appearing, is literally just 1/2 times the second time derivative of this mass moment with two indices, ij. That's a funny thing, right? Remember, this was essentially rho, so the mass energy density times xi, xj, but we're also going to subtract essentially its trace from it. And that's what defines the famous Newtonian mass quadrupole moment that Matthias also was writing on the board today. Yeah, so already here we see in the lowest order expansion, in standard linearized gravity, this is the thing that appears. But they're high order corrections, and these are the ones we're really, really interested in. Yeah. So in summary, in the TT gauge, in the quadrupole approximation, so leading order, all we have as a gravitational wave is essentially 1 over the distance to the source, and then the second time derivative of this quadrupole moment evaluated at the retarded time, which also makes sense, right? What I observe at future null infinity will have been generated by the source, but then of course it's traveling at a finite speed, at the speed of light, until it actually reaches the observer. So that's why we're interested in the retarded solution. Yeah.
I don't know the derivation.
Okay.
Could you remind us what lambda?
Yeah, this is just a projection tensor to project into the TT gauge, essentially. That's all it is. Yeah. It's just a projection operator that selects the TT component for you. Yep.
In your recurrent phase function, well, that is a static one. How do you incorporate time derivatives?
Time derivatives.
Yeah, so in general, like that.
Sorry, I'll go back.
An expansion. This is like the first time, right, where you neglect by well, coming from the relativistic phase function, do we have like?
That's right.
Yes. So I wonder, like, in this approach, how we incorporate the time derivative.
Well, it doesn't, right? Because it would be higher order here.
So we can say
it would not be leading order.
Oh, so like in principle, do you have those terms there?
I'm pretty sure in principle, but yeah. This is something, of course, that's in linearized gravity, right? We also pretend like the gravitational waves are not doing anything at all, right? They're just traveling in a background space-time that is fixed. We're also assuming that nothing's actually happening to the source, right? It's just moving on geodesics in Minkowski space.
You put it like the first question. Well, those derivatives are time derivatives are needed to obtain the right. So I was just wondering in this approach how you do that too, right?
I have to think about that. I'll get back to you. Okay, and then the other thing that kind of falls out of nowhere, if you have ever looked at linearized gravity, is the flux or the gravitational wave luminosity. So the energy radiated over time in gravitational waves, which you also were introduced to this morning, which is proportional to the square of the third time derivative of the quadrupole moment. And you can define analogous ones also for the angular momentum flux and the linear momentum flux. Yeah, just the main thing is at leading order. So in the classic Einstein quadrupole formulation, you find that the flux is this term. And I've highlighted this in yellow here because that will be quite interesting when we later do counting in PN theory, because you notice this is 1 over c to the 5th power. So it's actually quite high, right, in terms of powers of this, the speed of light. So do remember that for later on. All right, now what we want to do is we want to go beyond that. Linearized gravity is not good enough for waveform templates. People realized that very, very early on. And as I've just said, we have effectively assumed that we have the particles moving on geodesics and Minkowski spacetime. So no back reaction. So that would never actually cause an in-spiral in that sense, right? So to say. So how do we kind of self-consistently evolve a picture that gives us the dynamics of the binary, the emitted gravitational wave, and the decay of the orbit over time as the radiation is being emitted? And so the kind of classic picture that we use in that approach, as I said, there's other ways, but in the classic PN-PM way is the following. And it's based on essentially a separation of scales. So your picture is you have your source here, which has some characteristic scale D. Could be the separation of your binary. If you have an individual object, right, it could be its individual size. But in our case, right, separation, which we just denote here as D. So that kind of defines the sort of very near zone to the binary, but we've defined a near zone a little bit bigger than that. So a little bit outside your binary, and then this whole range here we call the near zone. Then we go super far away where our observers are, and we observe the gravitational waves at future null infinity, right? They travel along the light cone. That's where we're going to observe them. And that zone we call the wave zone. And that is, of course, characterized essentially by a distance that is larger than the wavelength of the gravitational wave that's being emitted. And then there are kind of these intermediate regions here. There's this region here where we are somewhere between this sort of slightly extended near zone, but still smaller than the wavelength of the gravitational wave, slightly extending also into the wave zone, and that's what people often call the exterior region. And then there's this green region here. And this green region is very, very interesting. That's sometimes referred to as the buffer region or the matching region. And I know there's some PN experts in the audience. And this is where really the interesting magic happens, in my opinion, where you connect your near zone dynamics essentially to your observables at future null infinity by expressing the multipole moments. And so that's kind of the important bit here. So what you need is equations of motions, so some description in the near zone, which eventually gives us the metric in the near zone, which tells us how the objects move. We need the generation of the waves and how it links to what we observe at future null infinity. And then we also need to take self-consistently into account the back reaction onto the source. All right, so as opposed to flat linearized gravity, right, we had a fixed background. We no longer have this now. So we're going to change our assumptions on the underlying problem. We have still slowly moving sources, right? So the ratio of the velocity of our objects over the speed of light is less than 1. We assume that they're weakly self-gravitating, but they are self-gravitating and stressed, weakly stressed. And we have our source being confined, right? So it has compact spatial support and is smooth, so literally mathematically meaning C infinity in there. We also assume that our source is isolated, meaning at some point, right, in the past, it wasn't perturbed by something else, but it was just stationary in the past. And that is kind of a reframing of this no incoming radiation boundary condition that people use. So that kind of what goes into it as a sort of basic thing. We define an expansion parameter, which is the ratio of the velocity over the speed of light, which you can also express in terms of the mass and the size of the source. And we say this is much, much less than 1. And so what we want is eventually what we had in linearized gravity, but now we're going to include higher and higher order corrections to the Newtonian equations of motions, because effectively that's what we had in linearized gravity, right? We had Newtonian type equations of motion, but now we're taking this consistently into account and link it back to the generation considering these PN sources. Yep. Well, it means that, again, we are not where the two objects are really, really close to each other, and you can describe this effectively, by a very strongly gravitating object itself. Now, the natural starting point are not the linearized field equations in this case, but people start from the relaxed Einstein field equations, and that is also known as the Landau-Lifshitz formulation of general relativity, where we define a gravitational field amplitude, which we also call h mu nu. You sometimes see a slightly different letter in the literature, which is defined. It's a definition in that way. So we have here the determinant of the covariant metric, and then we have the contravariant metric minus a Minkowski-like auxiliary flat space metric here. As before, we are free to choose a gauge, as always, right? In GR, pick your coordinate system. People traditionally use the harmonic gauge. You'll also maybe find some expressions in the ADM gauge or other things, but we'll stick to the harmonic gauge, which translates into exactly that, right? D nu, h mu nu equals 0. And if you, again, just take this definition, go and plug it into, so you calculate your Riemann tensor and everything, you plug it back into your field equations, and they reduce down to something that looks very, very similar to what we've seen in linearized gravity, right? So we have the D'Alembert of this h mu nu equals 16 pi g over c to the 4th, and then we have a new stress energy tensor on the right-hand side here, and that is now tau mu nu, and that's in fact a pseudo stress energy tensor. Why? Because it now does not only take the matter fields into account, which is what we had before, right? We just had our standard matter source, but also the fact that in the space-time, right, I have a gravitational field. So I don't have a fixed background anymore, like we assumed before. But I've got gravitational field energy and energy coming from some source that is sitting there, right? Some object. So it's both taken into account here. And you can go and calculate that. So exercise if you're interested. Take this and work it through and calculate the gravitational field tensor, which you will find is essentially something that depends on our gravitational field amplitude as h squared, h cubed, h quartic, and so on and so forth, right? But it doesn't start at h, it starts at h squared, which is probably also not too surprising, right? Now, we had a wave equation as before. Again, we know how to solve the wave equation, right? So we again apply the appropriate Green's function technology, so to say, to it. So we have to integrate over the spatial volume here of our source. But of course, now on the right-hand side, we don't have just our t mu nu, but we have tau, right? We have this more complicated source that includes both the gravitational field itself and the stress energy tensor of the source that you need to integrate over. And again, it's the retarded solution that is being selected because we assumed it was stationary in the past, right? So in that sense, it was an isolated source. And now the question is how we're going to solve this. This thing is very complicated, right? It's clearly nonlinear, has all sorts of stuff in there. So how are we going to solve this? And this is where the separation of scales now becomes very, very handy, because there are two scales in that problem, right? As we have seen, there's whatever happens near to the binary where things are actually moving versus very, very far away where some observer who's going to observe the gravitational wave. And so we split this literally into the far zone and the near zone. And then we need to match these two regions together. So let's start with the far zone, because I think that's the one that's probably a bit more intuitive, so to say. So picture here, we have our gravitational wave source, characteristic size was d. So in this case, could be the radius of the orbit of our compact binary. Observer, very, very far away in the distance. We have the position vector to the observer x, right, which translates its norm into r, and the normalized unit vector along this direction is just n. Yeah. Now, if we're very, very far away, and we think about the definition of our source tensor here, what's going to be out there? It's going to be dominated by the lambda term and not by the t mu nu term, right? And that's exactly what you do, right? So in the exterior region, it had compact support. That was one of the key assumptions we made. So it's not stretching out somewhere. It's very localized, so we can neglect it. And then our equation, our field equation, actually translates into the D'Alembertian h mu nu equals just this lambda mu nu, right? So the gravitational field term, that's the only thing that remains. And the energy momentum conservation equations are the one of flat space. And that's very nice, especially if we remember that our lambda term here, the gravitational field tensor, starts at h square order. So it turns out that one can show, if you go to the classic paper by Blanchet and Demont, that you can solve this equation in a so-called non-linear post-Minkowskian expansion. And so post-Minkowski here means, as you would think, you perturb Minkowski space order by order in terms of this gravitational field amplitude tensor h mu nu. And the general solution should then read as the sum over these perturbations, where in the bracket here, this denotes the order of the perturbation. And our bookkeeping parameter here is the gravitational constant g. So this is your, there's a theorem that has been proven that this is your general solution to this equation that was shown on the previous slide. Now, if we do that and insert it into our wave equation and equate it order by order, then this is what we find, right? We find kind of this ordered wave equation order by order in H. And then on the right-hand side here, we have the order by order expansion of the lambda tensor. And that will depend, remember, starting at H square. So think about the combinations, right? And so we'll go up to n-1, but obviously at second order here, right? This will only depend on the second term, but in its linear expansion. Otherwise, you'll be counting to higher and higher order terms. So keep your orderings in place, so to say. Now, what's also very nice is you see the leading order term, right? The linear term vanishes. And that's a consequence of the fact that our lambda tensor is quadratic in H. So obviously, if there's no quadratic appearing there, it has to be 0. So from that, it was shown that you can solve this type of equation by means of the multipole expansion in this exterior region. And in fact, the general solution is essentially a sum of retarded multipolar waves. And that was shown in the very famous paper by Kip Thorne in 1980. So we can write down the solution at linear order in H as the sum over, and then these are derivatives here, of some function KLF over the radius. Now, notation. This is like funny notation that people often get confused by. So this capital L here is what's called a multi-index, and it's only for spatial indices, right? So let's assume little l is 2, right? And we're counting up to second multipole term in the expansion here. Then that would be a di dj. Okay, it's just 2 things here. So just, I hope that makes sense to everyone. So that's kind of how you count here. Now, it's not so much important in terms of the details what this function KL here is, but it turns out that it is, without loss of generality, a symmetric and space-free tensor. And in fact, we'll find out later on that this is connected when you make a particular gauge choice to the source multipole moments. And that should hopefully not be surprising, right? At linearized gravity level, we wrote our H down in terms of the quadrupole moment. So I hope nobody is surprised, right? That if you generalize that formalism, that you'll also find a connection to the source multipole moments. Eventually, right, if you reduce your assumption down to linearized gravity, you should recover, of course, linearized gravity in that limit. Yeah. The other thing you notice is there's a 1 over the distance, which means inherently this is going to diverge as you take r to 0, which is also not too surprising because we are in the far zone, right? So, but that's also quite crucial to remember. You can't just take that as is and just apply the same thing to the near zone. That's not going to work. So now those are the main key things to take away. Now, these are 6 functions which can be shown to be related to these source multipole moments, where I are the mass type ones and J are the current type ones. And then there's 4 other ones here, which are, turns out, just gauge moments, which means you can gauge them away very nicely. And so it can be shown that you can transform this now into a metric that only depends on two remaining multipole moments, and these are what's called the canonical. So there's an isometry. You can map the metrics, and then you just have these two left over, which is probably also not too surprising. Now the question is how you actually determine those, and that will be quite crucial. Yeah. And the answer is through this matching procedure. So that's why this matching is really, really important. Now this was the leading order term, right? This was H1. Now you want to do this up to Hn, whatever your desired multipolar order is. And so it can be shown that you start from this as a seed and you iteratively construct the higher and higher order NPM metric, as it is called. And so schematically, right, you have this particular solution that you need. You need to construct a homogeneous solution, just like you would generally do. 1 second. And then you combine them together to get the full solution. That's very schematically. The details are pretty full on, if you ask me. That was a question.
Yeah. So how did the gauge moments arise?
How did the gauge moments arise?
Yeah.
Yeah, so there's a gauge freedom you have when you write these down explicitly, and when you apply it and you work it through, it turns out that you can literally, they become zero. All the other ones, the W's, X, Y's, and Z's, and the only ones that are remaining are these I and L's, but not in the form of ILN in this form, but slightly modified, and that's what these canonical gauge moments are. So you need to find a map eventually to relate them back to your I's and your J's, which are the ones we are familiar with.
And in each order, there should be new gauge moments.
Nope, these are the full. These are the full, because you have 4 gauge functions, right? And that's all, so you're left with 6. That's right. And then you can reduce these 4 remaining ones down, and you're only left with the 2, the mass and the current type ones, and the other ones are gone in the right gauge. All right, so you iteratively do this, and then in principle now, that sounds very easy. It is not, right? If you look at the papers, you have constructed your full metric now in the exterior region as a complicated function of these source type multipole moments. Now, what we're interested in is if I go from the exterior region very far, right, to future null infinity, which is where I'm eventually going to observe my gravitational waves. So taking R to plus infinity. And it can be shown, and again, there's a proof for those interested, if you want to look it up, that the general structure of the solution at the NPM order is given in this particular form here, where we have a new set of multipole moments arising here. But what you notice is the log terms here. And nobody kind of likes log terms, but it turns out we don't need to worry about them, because again, they are actually an artifact of the choice of coordinates we have made at future null infinity. And if you choose a better choice of coordinates to go away from your harmonic coordinates and transform into actual radiative coordinates or bonded type coordinates at future null infinity, then these logs disappear. And you get actually quite a simple structure of your waveform, right? Which is, again, here along the line of sight, so the direction to the observer. Here we have 1 over the distance. And then we just have these multipole moments as a function of the retarded time in the radiative coordinates, which I've now called capital U here. But the structure should look very familiar to what we have seen before as well, right? So if we compare that back to Hij in the TT gauge, that looks all hopefully reasonably familiar to you, just in a generalized form up to the nth order that you may want to consider. Now, it turns out that these new functionals that were appearing here, these k's here, right? So they are functionals of the source multipole moments, but not in a direct way immediately. And they lead to a natural definition of what's called the radiative multipole moments. So if you're lost now by the number of multipoles, there's the cheat sheet down here, right? So the source multipole moments were the standard ones we know, where in particular the first 2 ones here are mass and current type, and then we have gauge moments, which we can gauge away through a canonical transformations, which leaves me these M&S moments. But when I go to future null infinity, my explicit functions actually become written down in terms of radiative multipole moments U and V. And the trick is, of course, to relate these here back to the source, right? So this is what we need to do. And that's kind of where some of the crazy stuff happens in PN if you ask them. Now, however, what is really nice, after long calculations, one can show that these radiative multipole moments, which appear, as you can see here, now in the asymptotic waveform at future null infinity, looks very similar to what we had before, right? So if, again, we project along the line of sight to the observer, so that gives us the TT gauge. And then we have these moments here appearing. And if you think back to the structure in linearized gravity, turns out then that your radiative multipole moments are related to the canonical ones by time derivatives. So L here at the top in the brackets denotes the L time derivative. And that looks maybe super complicated, but think back, right? How many time derivatives did we have of the quadrupole moment in linearized gravity? 2. Where does our sum start? 2. Exactly, right? So you can keep track of that, right? We're nicely recovering the limit as you would expect. Now, it's great that we can directly nicely relate them to the canonical moments, but eventually, of course, what we're really interested in are the source moments because they describe the properties of the source. Now, a super quick interlude on that. We can also write down the flux, the energy flux in our gravitational waves now in terms of these radiative multipole moments, in particular the first time derivative, as you can see here. And these are very long polynomial expansions that you can look up. But the key point is, as before, right, we have just generalized these things. We had the third time derivative of the quadrupole moment in the linearized approximation, and now we're going, to these radiative moments, but we'll see eventually how we can relate them back to the source multipole moments. And you recover something that has higher order corrections, but of course, that leading order should give you what you got in the Newtonian approximation. We've already heard before that we can define polarization basis, different conventions in the literature. Here we call them P and Q, and that allows us to take our asymptotic waveform and project out the 2 residual degrees of freedom, which are the 2 polarizations, H plus and H cross. And this is quite interesting because we can now also define the asymptotic waveform in terms of modes. And modes are going to be really important for gravitational wave data analysis. We don't do a lot with polarizations. We do a lot more with modes. So how do we define those modes? So it turns out, as Bruce was mentioning before, right, these are spin 2 fields. And so we can decompose them in the basis of spin 2 weighted spherical harmonics. These are these YLMs here, and these coefficients HLM. This is what we call the modes. And as you would hopefully have expected, you can rewrite them in terms of the radiative multipole moments. So if you have ever wondered about what the HLMs are, this is exactly what they are, right? They are given in terms of the decomposition of these radiative multipole moments. And you can nicely see also, as you would have expected, the connection to the flux. So do keep that in mind. Yep. On the YLMs, it's just the spin weight. Yeah, it's just a spin weight. So just denoting that these are the -2 spin weighted. So if you look at them, you'll find different ones for the different types of spin weights you have. Yep. That's the retarded time in radiative coordinates. Yeah, bad choice of notation. Very good. We should call it capital T _ RET. Very good. So that's the far zone. What about the near zone? What about the source? Now, this is where the name comes in of post-Newtonian, because now we're actually going to do the post-Newtonian expansion, right? So in the kind of near zone, you would say, well, the retardation effects are not really so important, right? Because I'm near the zone where things are actually happening. So we can expand, again, our retarded time, and we see this sort of multipolar expansion. But then we can do the same for the effective stress energy tensor around, T, time t. So plugging in the expansion here. So explicitly, if you do that, what you find is, okay, so my stress energy, my pseudo stress energy tensor at the retarded time is then the one at the present, so at the time associated with the source. And then we'll have ordered corrections in powers of c. And I think that answers your questions, right? As you can see here. And then we get time derivatives that are popping up in here. And so if you do that, there is again a theorem that says you can solve such an expansion in terms of an order by order series, as is kind of suggestive if we look at this here, by expanding the left and the right-hand side of our effective field equations, right? And so we're gonna do, and I'm gonna call this H bar here to denote the near zone now, so we're close to the source. We didn't have any H's when we were talking about the far zone, any bars. And so you find here, this is then my mth Pn expansion here, my order, times 1 over c to the power m. And again, right, if we're looking at the expansion here, we're now starting at m equals 2. And we do the same on the right-hand side for our stress energy tensor. And then the game is again to solve order by order, right? So you're equating terms that have now the same powers of c. So our bookkeeping parameter now is the traditional Pn bookkeeping parameter. So, you know, v over c to the power m that you have. And so what you find is you can rewrite this and you get a kind of recursive set of Poisson-like equations now, right? So Poisson operator here on the right-hand side. And then we have the source term where the bar, remember, denotes already our Pn expansion. So order by order, right, is what we're comparing left and right in the expansion here. And many, many, many pages later and many proofs and many subtleties because of the occurrence of divergences and because your Poisson integral is not actually bounded because you don't have a compact source, because remember, your tau includes the field as well, which doesn't have compact support as opposed to your matter distribution. And so many smart people have a lot of time to spend a lot of time to show that you can still solve this problem. And essentially this form here, where you have a term here that does not depend on any time integrations and is sort of kind of instantaneous in that sense. But then there is a second term to your solution, which again is a multipolar expansion. So you see the L's popping up here again, and here we have these multipolar functionals. But what you notice here is we have the standard retarded solution here, but then we also have an advanced solution here. And that's quite different to what we had in linearized gravity, right? We didn't have anything like that popping up in linearized gravity when we were doing that. And so this time asymmetric component here, this is what encapsulates the radiation reaction effect back onto the orbit, right? Which is what we didn't have in linearized gravity, where we ad hoc define some sort of effective energy at the end of it. Yep. How is there not a time integration here? And because it's coming, essentially, it's a redefinition of your Laplace operator, of your Poisson operator. So it's just an integration over spatial domain here. That comes into play here. Now, this gets a lot more complicated because you need to regularize the whole thing because there are divergences popping up in here. But that part of the integral itself is only an integral over d3x. That is for the bookkeeping of the order, because remember, right, your tau has row terms in there which are scaled by 1 over c squared. So that's why you have a different labeling. Yeah.
How do we interpret things?
Yeah, you can interpret it in the way that if you apply the standard D'Alembert, the standard flat space D'Alembert onto that object here, then you recover the solution to the source-free wave equation. That's how you can interpret it. Okie dokie. And with that, brings us to the last part, which is we now need to marry these two approaches together, right? In both ends, you hopefully noticed, right? We have somehow dependencies on these multipole moments here. But eventually, we all need to relate them back to the actual physical multipole moments, and those are our mass and current type moments, which eventually, if we write it out, will give us something like the quadrupole and the octupole, and so on and so forth, right? And so we do this through this matching procedure, where one formally says the multipolar expansion of my metric in the exterior zone, this was our post-Minkowski approach, equals my post-Newtonian expansion in the near zone, right? So this was this green region where we will say, okay, both of these approaches are valid here. So I should be able to stitch them together to work out what some of these functions are that we haven't fully been able to specify just yet. And that's exactly what happens. So from that, in a very complicated way, you can then eventually write these out and connect them back to the canonical moments. And remember, we already had previously that the radiative multipole moments are connected to the Elf time derivative of the canonical moments. And now we have connected the canonical moments at leading order, at least directly to the source multipole moments. So that's kind of how they are nicely connected together. Now, in practice, right, you might compute a particular multipole moment first and then relate it back to the other one, depending on what you have. So that's kind of, in summary, what we are doing in a very, very complicated way, right? So we're connecting this whole problem from the near zone to the far zone through different types of expansions in the exterior, in the near zone, and then by taking the limit to future null infinity and introducing radiative coordinates. And the matching really is the one that allows me to relate essentially the observables in the wave zone to the characteristics of the source in the near zone. So in a nutshell, and if this was all like super boring or you zoned out, this is the one thing you should take away. Yeah. And of course, there's a lot more subtleties, mathematical subtleties, regularizations that need to be taken into account, analytic continuation that is being used, etc. I should also say that there's a different approach. You don't have to do PN in that particular way. You can do it in a different way introduced by Will and Wiseman, where you directly integrate the equations. So there's also different mathematical formalism. The nice thing is, of course, people can cross-check their results to get the same answers, and sometimes also found out that maybe somebody made a mistake and was able to correct it, which is also really, really nice, I think. So applying this to compact binaries, your recipe is the following. You compute your near zone metric to the desired order, Pn order, that you want. And then you get your conservative equations of motion of the relative motion, because you're kind of interested in the relative rest frame of the binary. You determine your gravitational wave energy. You compute whatever multipole moments you are required to compute in an iterative way. And then we use the energy balance equation kind of in this Newtonian picture, right? What goes out of the system, of the orbit, right, is radiated in gravitational waves and vice versa. You compute that, and then eventually you plug it all back in, because they have computed all the elements that you need, in particular your multipole moments, to actually get your waveforms. And as I said before, there's a lot more subtleties. But schematically, when you do that, what you end up with is classical in the sense, not classical in the classical sense, but in the sense of Newtonian-like equations of motion that are iteratively corrected by post-Newtonian orders, right? So acceleration of the first body, for example, in your two-body problem, right? Well, there's just your standard gravitational interaction that you all know from undergrad. And then you have iterative order by order corrections. And you get that essentially for all the dynamical variables that you're interested in, right? If you had a spinning system, you'd have another one for spins and so on and so forth. If you only look at the conservative terms, so these were the terms, remember, in the PN solution that did not have an advanced and a retarded solution, just the conservative parts, which are the ones here that are at full orders. And then you can show that at least up to 2.5 PN, indeed, the radiated energy is, ta-da! Everybody should have an epiphany. We've seen this equation before. What is this equation? The quadrupole formula. Whew. Very good. The proof for higher order kind of is outstanding, but nonetheless, we do still use energy balance when we derive post-Newtonian approximates. I should note on the side here. Yeah, and so that's essentially your recipe, how this works and how you do it. Yep. There is no third power of C for non-spinning systems. There is one if you have spin. In practice, of course, we introduce coordinates, as always. So if you write this down, so let's consider for simplicity a circular binary moving in the XY plane here. Masses M1, M2, separation is now called R. Don't be confused. Separation now should be a D to be consistent with previous notation. So we can write down the relative separation vector right in the XY plane. You all know how this works. And then our motion, right, if we attach this triad to it, is simply described by the separation vector, the direction orthogonal to it, and the z direction, right? So it's just literally moving attached to the binary in the plane. And well, I can literally do time derivatives. Everybody knows how to do that, and write down what the equations of motions are here, right? Now, I know nothing about what these terms are, and what we're interested in is, of course, to write these down in a post-Newtonian sense. Up to 2pn, right, for a circular orbit, nothing happens. It's just going to be a circular orbit, right? We saw that the energy emission starts at 2.5pn, right? So nothing's going to happen there. It's just going to be a circular orbit. So how do we solve these equations? Iteratively. That's the whole point, right? It's an iterative expansion. It's essentially a Taylor expansion that we're doing iteratively. So if you start at leading order, you write down your Newtonian energy. The quadrupole formula, the leading order flux, right, goes as 1 over c to the 5th power. So we're starting with this. We're assuming energy balance, as we've said before. So at leading order, if I plug this in, the equations before, expressed in terms of the variables I have, I find an ODE for the decay of the orbit, and I find an ODE for the change of the frequency, right? So the second time derivative of the orbital phase phi. And then we substitute it back into our equations of motion, right? We rewrite those, and then we do the next order, right? We do this iteratively up to, well, as much as you can, essentially, which becomes harder and harder the higher you go in your PN orders. From the flux, right, after you've iterated your flux as high as you wanted, you compute the source multipole terms now in these relative coordinates. And these are pages of expressions. That's why I haven't written anything down here. If you go to 3pn, for example, it's like a page, roughly-ish. And what's particularly interesting, you remember in the expression for the PN expansion, we had this asymmetric term time. So 2.5pn gives you your standard radiation reaction, which was at leading order the quadrupole formula, right? But then there are tail terms or hereditary terms that occur at higher and higher order, which are from the self-interaction of the field that come up here. And this gets more complicated to compute. For those of you interested, Larry Kitters from 2007 has a really, really nice derivation of some of those at 2.5pn, I believe. And then eventually, after you've done this, you end up with your desired expressions. And I've put down here explicitly from the Kidder paper the 2-2 mode. So remember, this was our mode decomposition of the plus and cross polarization using the radiative multipole moments. And you'll see this is what comes out here. So we have here the phasing term. So we still need to solve our phase evolution equation to actually evaluate this, right? And our position, and here we have the post-Newtonian expansion parameters, which contains the frequency. And of course, for the frequency, I had to also solve before from the evolution equations. Yeah, so it's this complicated, connected system of equations that you need to solve simultaneously in order to get to your final result. And that's the example here for non-spinning circular binary at 3pn. Why does the order matter? Why not stop at 1pn, right? The accuracy really makes a big difference in the waveforms. And here you can see some figures that I stole from Alessandro Bonanno's presentation or papers. where you can see the energy, the orbital energy here at different post-Newtonian orders as a function of V. So this was the post-Newtonian parameter we also heard about this morning. And here we can see the flux relative to the Newtonian, so the quadrupole order, and how it impacts as a function of velocity, right? And so remember, energy balance tells me flux is related to the energy, to how the energy changes over time. And they look quite different depending on the P-n order that you include. And that will impact then how your phase evolution of your binary is going to look like, and will dramatically impact the accuracy of your P-n approximant. And over time, so I'm going to stop with this one here just to give you a flavor of where are we at the moment. So this is from recently compiled by the LISA consortium, who have looked at all the P-n terms that have been computed in the dynamics, and then also in the flux. Because remember, right, flux starts at 2.5 P-n. So if somebody talks about the 1 P-n correction to the flux, in absolute terms, they're talking about a term that is 3.5 P-n in terms of its actual size, so to say. And so you can see where the things have been calculated. This hopefully answers the question from the colleague before, that spins occur at 1.5 P-n order, but the non-spinning case does not have something there. And then we have terms that are only partially computed, and that calculation is ongoing. Yep. It is a good point. So it depends on what you mean, right? It's less and less important at the early end spiral, right? But as you go, what you're interested in, you want to push to higher frequencies, right? We want to really be able to evolve the orbit essentially deeper in the potential. And that's why the higher corrections are really important, right? So the closer you want to be able to describe your binary system, like physically, right? The closer they are, the more important the higher order corrections become. Yeah, so that's the point, because now the curvature is becoming more and more, right? I'm stronger in the field, I'm deeper in the potential. You can think about the metric expansion as essentially write it down in leading order is just your standard Newtonian potential. And then we have corrections to it that come from the actual gravitational waves themselves as well. Does that make sense? Somehow? That is the point you'll eventually reach. So as you've seen, right, these are 1/Cn expressions. So they are also non-convergent, right? As you go to higher and higher order. So in fact, the P-n solution becomes problematic the closer you go. And traditionally, you would stop at what is the ISCO, the innermost stable circular orbit, or a little bit before, if you're a bit more conservative than that. And really from that point onwards, things essentially blow up. You're hitting infrared divergences, I believe, that you're reaching there. And so it's really no longer a physical description, right? You're just encountering mathematical artifacts from the non-convergence of the series. And that's when you need to switch to something else. All right, and with that, we're gonna stop today, and we're gonna look at P-n approximants, EOB, and phenom on Thursday. Thank you.